Hi everyone, I hope you had a chance to watch a crash course video. It was designed to give you a little background and review some significant figures, issues, and also unit conversions. Hopefully a lot of that was not new to you. If it was, you may want to go back and really review some of the early chapters in Harris to get up to speed on it. So I want to go a little step beyond that in this web video today, and I'm going to talk about some of the particular units that we use in analytical chemistry that maybe you haven't seen in the past. So we're going to go through a couple examples real quick here. Alright, well hopefully you're pretty familiar with the term molarity. We've seen that many times throughout chemistry so far, and that, as you remember, of course, is moles per liter. I also wanted to bring your attention to the concept of formality. I'm not sure if you have seen this before, but this is generally referred to as prepared moles per liter. So what I mean by that is if you have something like sodium chloride, let's see if I got a pointer here. If you're making like a one molar solution of sodium chloride, what we know about sodium chloride, it being an ionic compound, that what's actually going to happen is sodium chloride is going to dissolve into sodium and chloride, cation and anions there, and so you don't actually have a solution of 1 molar sodium chloride. You actually have a 1 molar solution of sodium and chloride. But we'll refer to this, instead of referring this as molar, we'll refer to this as 0.0 formal. Okay. Now, we're not always great at doing this as much as we should. But if you do see that the formal notation, you'll probably see that a lot in the lab, that you should hopefully understand what that means. Okay. All right. So erase this here. The other thing I want to talk about is these units here of these mass concentrations. We'll talk a lot about a weight per weight. That's mass of solute per mass of solvent. Right? That's a weight per weight fraction. And another one is weight per volume, and that would be mass of solute per volume of solvent. Okay. So you'll see these throughout the lab frequently, and so you have to, oftentimes this mass of solute per volume of solvent is used a lot to prepare solutions, because that way you don't have to worry about density and factoring that in your calculations. All right, so a couple of units I wanted to talk about were, let's see here, ppm, ppb, and ppt. And as you might have seen before, ppm, if you're unfamiliar with it, it's parts per million, right? So what that means, this is a mass concentration, and what we're talking about when we talk about parts per million is, it's going to be a way to do this quicker, is 1 gram of let me do that again, sorry about that, 1 gram of your solute over 1.0 times 10 to the 6 grams of solvent. Okay, so that's what we mean by parts per million. And so if we think about this if we sort of invert this, right, you could think of it as 1.0 times 10 to the minus 6 grams of solute per 1 gram of solvent. Okay. All right, so hopefully that makes sense. And so just to clarify that, again, that's 1.0 times 10 to the minus 6 grams of solute over 1 gram of solvent. And in conventional terms, this is actually a microgram. and this is a gram. All right. So you see, and if we remember that if the solvent is water, then our density is 1 gram equals 1 milliliter. So this will actually be microgram. Oopsie. Micrograms per milliliter. All right. So again, that's parts per million is micrograms per milliliter. And you can also think if you multiply both of these by 1,000, this is also equivalent to milligrams per liters. Okay. So you'll see these all interchangeably. Parts per million, just remember micrograms per milliliter and milligrams per liter. If we go back and we think about, let's see if I can go back here. If we think about our prefixes here, right? You're going to see these a lot throughout this class. So, in particular, ones I would say of particular interest are these right here, where we go to, let's say, 1,000. All right. So hopefully you all can become pretty familiar with these. So nano, micro, milli, these ones in particular, and then also kilo. All right. So these are the ones that we're using a lot, occasionally centi. So be able to do these conversions. Hopefully this will all be really familiar to you. If you haven't seen it before, you might want to review this. These are things that you probably will need to know in the back of your mind. Okay, so again, that was parts per million, and parts per billion, as you imagine, is just the same. So I'm going to get rid of this. This equals parts per billion. All right. In this case, instead of it being 1.0 times 10 to the minus 6 grams of solute per gram of solvent, we have 1.0 times 10 to the minus 9 grams of solute per gram of solvent. So this is also seen as, again, if we remember, in this case we're talking about nanogram, and this is a milliliter, so this equals 1 nanogram per milliliter. And again, if we multiply this by 1,000 each side, we get micrograms per liter. Okay, so you may want to go through those calculations yourself, again, referring back to those prefix tables, so you'll be able to recognize all these units. And again, so I apologize about my handwriting on this. I'm still getting used to using this tablet, so bear with me a little bit. All right, and then finally, parts per trillion. Right. So this one is just an extension of what we've seen before, right? And that is, again, out of this case, we're dealing with what's going on here? 1 times 10 to the minus 12 grams per gram. And if you go through it, you'll see that this is actually a picogram per milliliter, or a nanogram per liter. Okay, so hopefully these things are familiar to you, and these particularly these ppm, ppb, and ppt, these are really commonly found in environmental applications. Dealing with pollutants, oftentimes you're looking at things that are in really low concentration. So just to give you guys an example of this, I'm going to run through a quick calculation, and from like a practice problem, we'll see how this looks. So hopefully you all are following along. Okay, so if we go here, okay, so here's a question I might ask you, and that is, all right, what's the molar concentration of mepropamate in drinking water found from this table here? All right, so this table comes out of literature, and you can see here mepropamate. So these are all pharmaceuticals and waters. It's actually sort of interesting that, you know, as humans take more pharmaceuticals, they end up being excreted, and they end up in the wastewaters, and then they go through a treatment plant, and so they eventually will end up back in the drinking water that we're all seeing. So if we look here, whoopsie daisy, where are you? There we go. So we got mepropamate. If we look at it in the finished drinking water here, you can see that we have approximately, there we go, it's 5.9. If we look at these units up here, This is nanograms per milliliter per liter. Okay, so we got 5.9 nanograms per liter. All right, and so one thing you want to do before you start here is, let's see if we can. Before you start here, is you want to find the formal weight of meprobamate, because eventually you want to know what the molar concentration is here. Okay, so the formal weight, if you look this up, go on Wikipedia or something like that, or the Sigma Aldrich catalog, is 218. Sorry, 0.25 grams per mole. Okay, and so we're starting out here. If you remember, we have 5.9 nanograms per liter. All right, so start here. It's a 5.9 nanograms per liter, right? And we want to convert this eventually into moles per liter. So the first thing we want to do is get this into moles. So we say, okay, we know that there are 10 to the minus 9, or so 10 to the 9th nanograms per 1 gram. All right, so this will convert us from nanograms to grams. And we want to go from grams per liter then to moles per liter, so we want to use our formal weight here. So we say this is 218.25 grams per mole. If you go through this calculation, you just go through it and we calculate and we solve, and we find that our concentration of meprobamate in drinking water here ends up being 2.7 times 10 to the minus 11 molar. Okay. And so if we wanted to use an easier prefix, this would actually be 27 picomolar. All right, so not a high concentration. That's P. Sorry, that's P. All right, and so hopefully y'all can see how we were able to convert from this common analytical term here in the environmental situation, nanograms per liter, to molar concentration. If you remember, if we go back and we look back at our previous common concentration units, if you remember, parts per trillion, right, is actually a nanogram per liter. All right, so what we did was we essentially went from 5.9 parts per trillion, which ends up in this 5.9 parts per trillion in the case of meprobamate, ends up being equal to 27 picomolar, or 2.7 times 10 to the minus 11 molar. So, all right, well that's it for this pre-lecture video for Monday. So hopefully y'all were able to follow along and just give me some feedback when we get into class, and we'll see how things go, and we'll be ready for our whole goal assignment on Monday, which will be dealing with errors and their effect on data. So have a good weekend. See you then.